Right, so where we stand at the minute, we've gone through a lot of the stuff on here. Really, we're left just with the bit at the bottom, tangents and normals to have a look at. And before we get to that for our conic sections, we just need to expand our ability to differentiate a little bit. So we're going to be having a look today at implicit differentiation. So just first of all, to go through what we mean by implicit relationships. So whenever we can't just say y equals 2x, y equals 4x squared plus 3x minus 2, we can't write y explicitly in terms of x, or vice versa. We say we have an implicit relationship. When y can be written as a function of x, like the example I just mentioned, we have an explicit relationship. So this means that the sorts of things that we've been looking at recently with conic sections, they are generally implicit relationships. Okay, that's what we've been looking at. So we've got here for the circle, we've got no simple way of saying what x equals in terms of y or y equals in terms of x. And similarly for the hyperbola, the way these relationships are expressed, they are expressed implicitly rather than explicitly, saying what y would be if we know the x value. Of course, we can work out what y could be if we know an x value, and often there's more than one answer on these things. Now, before we get into implicit relationships, I'm just going to rethink some of the stuff that we've done about differentiation in year 12. Okay, so when you see y equals x squared and you differentiate, you probably just think you're just differentiating the x squared, and that comes down to give you 2x. In fact, though, you're differentiating both sides of the equation y equals x squared with respect to x. Yes, we differentiate the right-hand side, that gives us 2x. When we differentiate y, that gives us dy by dx, the derivative. Okay, so in actual fact, what we are doing when we're differentiating, even when we have an explicit relationship like this, we are differentiating both sides of our equation with respect to x. Y differentiates to dy by dx, x squared differentiates to 2x. So we can think about differentiating both sides of an equation, all right, when they may be given explicitly, implicitly, like these ones are. So let me take a pen. We start with the first one. If we've got 3y and we differentiate that, well, we know if we differentiate 3 lots of something, we get 3 times the derivative. We know that y differentiates to dy by dx. So here, when I differentiate that side, I get 3 dy by dx. And when I differentiate the right-hand side, the 2x goes to a 2, and the 1 obviously differentiates to 0. Constants differentiate to 0. So we've differentiated both sides. Yeah, 3y goes to 3 dy by dx, and 2x plus 1 goes to 2. Let's try this one. 5 equals x plus y squared. Differentiate both sides. The 5 goes to 0 because it's a constant. The x differentiates to 1 because it's just x. Now, y squared, we need to think about this a little bit now. What we have here to do is, well, really, if we think about it, it's the chain rule. Okay, the chain rule says if we're differentiating a function of a function, we differentiate the function with respect to the variable itself, and then we put the derivative on the end of that. So that's a bit of a clumsy way of just saying that if I want to do dy by dx, yeah, I can do dy by du inside function, and then times by du by dx. That's usually the way that you see the chain rule written down. Okay, that way around. So actually, what I can do here then, let's think about it slightly differently. We're trying to differentiate here the y squared with respect to x. All right, so let me think about it this way. If I want to differentiate y squared with respect to x, what's that going to be equal to? Well, the chain rule says I can differentiate it with respect to y. All right, we're going to differentiate it with respect to y, and then we can multiply by dy by dx. Okay, that's just a chain rule. Look, all that's happened really is instead of differentiating by u and the du here as well, we've just put a y there and a y there. Yep, that is just a chain rule. That's just what it's saying. And we're left with dy squared by dx. Well, if I differentiate y squared with respect to y, I know that gives me 2y. And then I have to put dy by dx on the end. That is what the chain rule is just saying to me there. Okay, so I differentiate the y squared with respect to y, and then just put dy by dx on the end. That is the chain rule. All right, so whenever you see a function of y, just think differentiate it with respect to y, and then write dy by dx on the end. That will be what it differentiates to, because that's what the chain rule is telling me. Differentiate it with respect to y, and then write dy by dx on the end. Okay, let's come to this one then. X squared equals 3y squared. Differentiate with respect to x on the left, and on the right, based on what we've just been doing, differentiate with respect to y. 3y squared would go to 6y, and write a dy by dx on the end. Okay, getting the idea? Let's go to the next one. X squared will differentiate to 2x. Y squared, we differentiate with respect to y, and we put dy by dx on the end. The chain rule again. And the one, constants differentiate to 0. All right, this big thing, take the left-hand side. 3x cubed is going to give me 9x squared. 5y squared with respect to y would give me 10y. I'm going to get a dy by dx because I differentiate with respect to y first. The 12 is a constant, it differentiates to 0. And on the right, 5x differentiates to 5. 3y with respect to y gives me 3, and I have to write a dy by dx on the end. Okay, and our final one. Now it's helpful here to remember that the square root is a half power. So each one of those are really half powers. So I'm going to get differentiate with respect to x, a half x to the minus half, bring the power to the front, bring the power to the front rather, and knock the power down by 1. And then the same with respect to y. And then we remember to put our dy by dx on the end. Oops. Our dy by dx goes on the end, and we had a constant on the right hand side, so that bit gives me a 0. Oops, it's got rid of all of that. Let's bring that back so that I can just put the 2 back that was there. Okay, so each time what we've done when we're differentiating with respect to y, let's step them through. The 3y squared, let me change my pointer. So the 3y squared here, differentiate with respect to y, 6y, and write dy by dx. The y squared here, differentiate with respect to y, write dy by dx. The 5y squared here, differentiate with respect to y, write dy by dx. The 3y, differentiate with respect to y, write dy by dx. Square root of y, differentiate with respect to y, write dy by dx. And what we've just done there is called implicit differentiation. Okay, basically we're using the chain rule. Whenever we're not seeing a function of x, we're using the chain rule and writing dy by dx. Okay, that's implicit differentiation. So when we differentiate a function of y with respect to x, we differentiate with respect to y and put a dy by dx on the end. So as I've written it there, if we're differentiating a function of y, differentiate the function with respect to y, write dy by dx. Now, one term that's quite useful to know about at this stage, although it's getting a little bit ahead of ourselves because we've not done this other particular rule for differentiation yet, is that quite often we might have to differentiate the product of x and y. It appears quite a lot in implicit differentiation questions. And this will occur, by the way, later on in one of the externals. Okay, when we're dealing with implicit differentiation a bit more in the round, that will be on one of the externals, but it's needed here a little bit for the conics. So when you differentiate a product like that, it needs a product rule. Now, we'll come to the product rule a little bit later on, but this particular result that comes from the product rule is quite useful to know. If you're differentiating the product of x and y, we first differentiate x, gives us 1, and leave the y alone. And then we add to that, leaving the x alone and differentiating the y. All right, so we get differentiate the x gives us 1, leave the y alone, that's still y. Leave the x alone, and then differentiate the y gives us dy by dx. So the derivative of xy is y plus x dy by dx. We'll come to why that is the case later on when we look at the product rule, but it's quite a useful one just to know now, just drop into some of the questions that we're going to do. All right, so let's have a look at some examples. So these ones are going to go a little bit further. We're going to want to rearrange and say what dy by dx actually is at the end. So we're going to do the implicit differentiation that we were just doing, and then right at the end we're just going to rearrange so it says dy by dx equals. So it will all become clear. We do this first one. So we differentiate, first of all, both sides with respect to x. So I will get a 3x squared. The 3x will go to 3. The y squared, if you're ahead of me on this, differentiate with respect to y to 2y dy by dx plus 3 dy by dx, because we differentiate with respect to y, don't we? And have to write dy by dx afterwards. And the 6 gives us 0. It's a constant. Right, what I'm going to do now is collect together the dy by dx terms, leave those ones on the left-hand side, and take all these other bits here across onto the other side. Okay, so I'm left with a 2y dy by dx plus a 3 dy by dx equals minus 3x squared. Got to take away the 3x squared, haven't we? And minus 3. I'm going to take away the 3 as well. Now what we do, we factorize here. If you notice these two terms, the reason why we've kept the dy by dx terms on the left is because dy by dx is a common factor. So dy by dx, the first term, I've got 2y plus a 3. 2y plus 3 dy by dx equals, and on the other side I actually have a factor as well, don't I? That I might as well take out 3 negative x squared plus 1. So if I now divide by the 2y plus 3, I've got an expression for dy by dx. dy by dx is going to be equal to the minus 3x squared plus 1 minus 3x squared plus 1. That looks a bit like a cube, doesn't it? So let's just my clumsy writing with a pen on here. So make that a 2. Divided by the 2y plus 3. And that's answered the question. We've written dy by dx in terms of x and y. Right, let's try the next one. The next one is a hyperbola. Again, just differentiate both sides with respect to x. 4x squared is going to give me 8x when I differentiate. And my 9y squared will give me an 18y dy by dx, yeah? Equals a 0. Constant. All right, do the same as we were doing last time, but actually this time I might think about the dy by dx as being on the right-hand side. Doesn't really matter, I can make it all negative and change it around, so because usually I'd prefer to have them positive here. 18y dy by dx will be equal to 8x. All right, convince yourselves that that's okay. What I've done there, really, I've taken the 18y across onto the right and left the 8x there, but then I've just swapped what's on the left and what's on the right because I can write an equation either way around. I can think here that I can do a bit of cancelling. So I'm going to change my ink colour. The 18 there is divisible by 2, so make that a 9. The 4 there is divisible by 2, the 8 there is divisible by 2, make it a 4. And we go back to our red pen. Now divide by 9y, and I'm left with what dy by dx is. So for that particular hyperbola, the derivative, the gradient function, is 4x over 9y. All right, a bit easier than the first one, really, isn't it? But that's showing us how we can get the derivative, the gradient function on a hyperbola. Not too difficult. All right, start with a slightly longer question. We've got an ellipse here. Okay, we've got its equation. We need to find an expression for dy by dx in terms of x and y to start with. So that's just what we've been doing. So let's start with our differentiating both sides. The x squared will go to a 2x. The 2y squared will go to a 4y dy by dx. Yeah, differentiate with respect to y. Write dy by dx. The minus x will go to a minus 1. And the 4y differentiate with respect to y and write dy by dx. The 6 on the right-hand side, again, is a constant, differentiates to 0. All right, so we need to just rearrange that so that it says what dy by dx is, because that's what we're asked to do first of all. So we'll take the 1 and the 2x onto the other side, and I've got 4y dy by dx plus 4 dy by dx and everything across the other side. So the minus 1 is a plus 1 on the other side, the 2x is a minus 2x on the other side. And now we take our dy by dx out as a factor again, like we did in the first example, because it's in both places. Dy by dx can come out as a factor. And what did we have? We had 4y lots of it, and a 4 lots of it, equals 1 minus 2x. So that is going to tell me that dy by dx equals 1 minus 2x. And actually, I'm going to factorize the bottom. I know it's 4y plus 4, so why don't I just write it as 4y plus 1, 4 outside the bracket. Okay, that's the first part done. It's now asking us what is the gradient of the curve at the point 3, comma, minus 2. So 3, comma, minus 2 is telling us there's a point on the curve. So let's just do it. The gradient function, dy by dx, tells us the gradient of the curve at that point. So when we're using 3 minus 2, let's put that in for dy by dx. So dy by dx is going to be 1 minus 2x, that's 1 minus 6, over 4 lots of y plus 1, 4 lots of minus 1. Okay, 1 minus 6 is minus 5. 4 lots of minus 1 is minus 4. So the gradient at that point on the curve is 5 over 4, or 1.25. Okay, just using the expression we got for dy by dx. That's what the gradient of the ellipse is at the point 3 minus 2. Okay. Then we come on to have a look at part B. What x value gives us a 0 gradient? Well, if the gradient is going to be 0, let's have a look at our gradient function. Let's come back. Our gradient function is here. What would make that 0? We're looking at the top of my fraction. I should be able to see there is a value of x I can put in there that makes the numerator 0. And if the numerator is 0, the whole fraction is 0. Doesn't matter what the denominator is. What makes 1 minus 2x 0? Well, We can write it out longhand if we want to. So 1 minus 2x would be 0. Well, that's only going to happen if x is a half. Now remember, this is an ellipse. There should be 2 points given when x is a half. And if you think about drawing an ordinary ellipse, if I just sketch one out here, okay, there's my ellipse. Actually, I don't want to put that. I don't want to put that line in there, do I? Because I can't say where the center is. But what I do know is that there should be 2 points on my ellipse where the gradient is 0. Yeah, because really that's going to tell me there and there. Okay, 2 points where x is a half will be on that line. All right, so the gradient is 0. I get horizontal tangent. And then part C rather, that was part B. It says at what y value on the curve is the gradient undefined? Okay, what y value on the curve is the gradient undefined? Now the gradient is undefined. We say gradient is undefined, if you remember, when we've got vertical tangents. The gradient is undefined because there we don't get a rise over a run. And actually it'd be undefined whenever we end up dividing by 0. If we end up dividing by 0, we can't do that. That's undefined. But we should be able to see that our denominator here is going to be the thing that we need to watch for. The denominator, if that becomes 0, we've got a problem and we'll get an undefined gradient. We'll get a vertical tangent. So we should be able to see that just means y plus 1 would have to be 0. So I can say then that in that case, y plus 1 would have to be 0. Which is going to tell me that y is minus 1. So when y is minus 1, I get those vertical tangents. This line here then is y equals minus 1. All right, we've said x is a half, is that line, because that's where we get those horizontal ones. And we've said here, this line is y equals minus 1. We've got the major and the minor axes. We've got the axes of the ellipse. What have we found out? Well, we can also then say that the center, can't we? We could say that the center is a half minus 1. That would have been the center of our ellipse, because we can see that from the little sketch we've just done there, the way those horizontal tangents and those vertical tangents box our ellipse. Does that make sense? Well, maybe it does a little bit. If you go back to our ellipse, let me go to my pointer, my original thing. I've got x squared minus an x. Well, if I was going to complete the square in that, wouldn't I have x minus a half? Yeah? In the square bracket. And because I've got 2y squared plus 4y, take the 2 out, I'm really dealing with y squared plus 2y. That's going to give me a y plus 1. So I get the minus 1 as the y coordinate of the center. All right, we'll just do this last one together, and then you can have a go at some. So if I just bring over my pen. So we've got here is the first one where we've got an xy together. So we've just brought this one in just to make some of the questions a bit more interesting, just a bit more general practice of implicit stuff, which will help with the external later on. And I've written up the formula there for what the derivative of xy is. Remember, it's y plus x dy by dx. So let's just differentiate. We'll go through this fully again. Let's just differentiate. I've got my pen, that's fine. So x squared goes to 2x. Y squared will go to 2y dy by dx, remember. Implicit differentiation. 10x will go to 10. 2y will go to 2 dy by dx. Differentiate with respect to y and then write dy by dx. And the minus 4xy, well, it's going to be minus 4 times what I've got in the bracket in the box up there. So it'll be minus 4y minus 4x dy by dx. And the 10 differentiates to 0 because it's a constant. All right, let's have a look what we've got in here. We've got 3 terms now that have got dy by dx's in them. So let's leave all those ones on the left-hand side, take everything else across to the right-hand side. So I'll have a 2y dy by dx plus a 2 dy by dx minus a 4x dy by dx is equal to everything else whipped across to the other side. Well, the only bit there that would become positive is the 4y then, because it was minus 4y on the other side. So I get 4y minus 2x minus 10. All right, at this stage, I might look through and say, everything's got a 2 on it, hasn't it? Everything is divisible by 2. So let's just do a little bit of cancelling before we do anything else. So let's just get rid of the 2 there. Let's get rid of the 2 there. Let's make that a 2. Let's make that a 2. That one's going to go, and that one will become a 5. So where are we back to now? We can just do our usual bit where we take the dy by dx out as a factor. That is an equals there. Just make sure that's clear. So we take the dy by dx out as a factor on the left-hand side. And we've got y plus 1 lot of dy by dx minus 2x equals 2y minus x minus 5. And then do the division. So dy by dx is equal to 2y minus x minus 5 all over y plus 1 minus 2x. I might rewrite it this way around just because I like having my x's and my y's first, but it doesn't really make any difference. And that's the first part. Okay, so that's that bit done. Second part's a bit trickier than we've seen before, because now we're looking at when is dy by dx going to be equal to 0. So this is a tricky question, this one, okay? More of the later external type of question, but if you can follow it, that's the good thing. All right, don't really need all of this for this particular example for the conic section, but it's maybe useful just to have a look and see where it's going to go. So I'm going to try and use as much space as I can on here. So let's just hide that bit off. Now, dy by dx is going to be 0 when the numerator of my fraction is 0. The numerator of my fraction is 0 means that 2y minus x minus 5 is 0. Notice this isn't straight away telling me a value for either x or y. But what it does tell me with a little bit of rearranging is that 2y minus 5 is x. So I know I'm on some kind of straight line. But I also know, coming back, putting a star here next to the equation of my curve originally, I also know that all of this is true for x and y. So all of that is true for x and y, but also x is 2y minus 5. Well, I can substitute that in. Okay, substitute it in. All right, you've done this sort of thing before when you've looked at solving quadratic and linear simultaneous. That's all we're doing here. Yeah, we can sort of kind of think of that as that's equation 1, the quadratic part. This is equation 2, the linear part. And we're just going to substitute for x into equation 1. So equation 1 is going to tell me that x squared, so that's 2y minus 5 squared. Remember, because we're substituting for x. Plus y squared, that's all okay. Plus 10x, 10 lots of 2y minus 5. Plus 2y. Minus 4xy. So I'll take the 4y to the front. And then I've got my 2y minus 5. I'm just running out of space a little bit here, aren't I? For the x part. That all equals 10. Right, we've got a bit of multiplying out, collecting together, having a look at what we've got, but hopefully you can see at this point we're going to get a quadratic in y. That's what we used to expect to do, aren't we? When we're dealing with quadratic simultaneous, where one quadratic, one linear, we're used to getting a quadratic equation to solve in the end, and that's where we're going to go. So let's just go through with this. So our bracket squared, 4y squared minus 20y plus 25 plus y squared plus 20y. Make sure that looks like a 2. Minus 50 plus 2y minus 8y squared plus 20y equals 10. All right, let's have a good look at that. There is some cancelling in there, I think, that we can do something with. So let's just do some cancelling like we would do usually. We've got a minus 20y and a 20y. They will go. Is there anything else in there that is going to go? 4y squareds. No, we've got some other y squareds kicking around. We've got a 25. No, not so much. So let's just stick with where we are now then. Go back to my red ink. So let's have a look at how many y squareds have we got. We've got 4, 5, minus an 8. So I've got minus 3 y squareds. Okay. Let's have a look at the y terms then. So we're just doing them in order. We've got a plus 2 and we've got a plus 20 there. Okay. Let's have a look at our numeric term. So we're going to have a 25. That'll take it down to minus 25. And don't forget we've got the equals 10. Don't forget we've got the equals 10 there. All right, let's take it all across to the right-hand side so we can make it a 0 here. And we've got a positive coefficient of y squared then. So we've got 3y squared. Yeah, minus a 22y. Plus 35. Because we had a minus 25 to go with our plus 10. All right. Does that factorize? Let's have a look. 3y, we're going to have to go this way if it's going to factorize, don't we? You could obviously stick this in your solver and your graphic calculator if you wanted to at this point. So we're going to get that. Now to get the 35, I'm thinking I'm going to need to do a 5 and a 7. That's the only way I'm going to get it. And actually that does work nicely for me, doesn't it? If I make them both minus 5, minus 7, I'm going to get minus 15 y's, and then for the middle one, I'll get another minus 7 y's, so that's okay. So I can say quite easily from there that y is either 7 over 3 or it's 5. And that's answered part B. All right, so that's just bringing in something that you've done before, looking at how you solve quadratic simultaneous. So that's it for our run through implicit differentiation. The key thing to remember is that whenever you're differentiating something with respect to x, if it's a function of y, differentiate it with respect to y, and then just write dy by dx on the end. There's some questions in Dr. Frost to have a go at. See how you get on. Let me know if you need any help, and we'll see you next time.